Hi everyone, this is Dr. Kiran, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Hyderabad, India. So, in continuation to the previous lecture, today we are going to discuss what is the temperature effect on diode current equation. So, let us directly go to what is the effect of temperature on diode current equation. So, usually there is a huge impact on diode current equation with this temperature. So, surrounding temperature may change the characteristics of a semiconductor diode. So, hence what happens, the diode current also changes. So, changes in the means it will increase because due to the temperature increment or increase in the temperature will generate the electron hole pairs. So, and hence your current also increases. So, before going in detail, so let us see what will be the current diode equation. So, I is equal to I naught into e power v by eta Vt. And what is I naught? I naught is the reverse saturation current. So, the temperature effect is mainly on reverse saturation current. Okay. So, I naught increases approximately 7% per degree rise in temperature. This is holds for the both silicon and germanium. I naught doubles for every 10 degrees centigrade rise in temperature. This is also important. Okay. So, due to the increase in the electron hole pairs, the conductivity, there is a movement of electron hole pairs. Okay. So, therefore, hence conductivity also increases. So, by that, so I naught also increases. So, I naught, how it increases? If I naught increases, I also changes. Okay. So, I naught doubles for every 10 degrees centigrade rise in temperature. Okay. And in order to maintain constant current, so we have to reduce or we have to change the applied voltage, input voltage. Here, the change in the voltage with respect to temperature, dV by dt must be minus 2.5 millivolt per degree centigrade for the constant current. So, in order to maintain constant current, we have to maintain dV by dt at a minus 2.5 millivolt per degree centigrade rising. That means the input voltage must be maintained like this. And another important effect, consequence with the temperature is barrier voltage decreases by 2 millivolt per degree centigrade rise in temperature. Okay, barrier voltage decreases. So, barrier voltage decreases means what? Current conduction. Barrier voltage decreases means depletion width will be decreases. When depletion width is decreases means current conduction takes place. There will be a current flow through the diode. And the relation between this temperature and reverse saturation current is given by this expression. I naught 2 is equals to I naught 1 2 to the power T2 minus T1 by 100. That means I naught 2 means what? Reverse saturation current of the diode at a temperature T2. And I naught 1 is what? Reverse saturation current at a temperature T1. Okay. So, therefore, this is because we know what is the value of 1.07 whole power 10 is approximately 2. 1.07 to the power 10. So, if you solve for this here in this diode current equation, so you will find this one. So, hence we can write I naught 2 is equals to I naught 1 into 2 power T2 minus T1 by 100. And this is holds for the both. This is common for both silicon semiconducting material and germanium semiconducting material. And so, with this we can say germanium can be used up to 75 degrees centigrade. So, it can withstand, germanium semiconducting material can withstand up to 75 degrees centigrade. Whereas, silicon can be used up to 175 degrees centigrade because of this temperature effect. Okay. So, let us do one problem on this. A silicon diode has a reverse saturation current of 7.5 microamperes at a temperature of 300 degree Kelvin calculate the saturation current at 400 Kelvin. Okay, so here it is wrongly printed. So a silicon diode has a reverse saturation current of 7.5 microamperes at a temperature of 300 Kelvin, and then calculate the saturation current at a 400 Kelvin. So here temperature is increased from 300 Kelvin to 400 Kelvin, and the reverse saturation current when 300 Kelvin is 7.5 microamperes. So we need to calculate I02. So I02, what is the formula? I02 is equal to I01 into e power T2 minus T1 by 100. So if you apply, sorry, it is 2 to the power T2 minus T1 by 100. So therefore, what is the I0 value? I0 value is 7.5. 7.5 micro, that is 10 power minus 6 amperes into 2 to the power T2 means what? 400 Kelvin minus 300. Okay, so if you solve for this, you will find, okay, so if you solve for this, I0 is approximately 7.45 into 10 power minus 9 amperes. That is I02 is approximately 7.45 nano amperes. So that means here temperature at one particular the reverse saturation current at particular temperature is 7.5 microamperes, and when you increase this, the temperature, the reverse saturation current I02 also increases. Okay, so therefore what we can say, the temperature affects on the diode current equation. So how to represent this on the VI characteristics? So this is, we know the forward characteristics of the diode. VF means forward voltage, and this is IF. IF means what? Forward current. Here it is IR, reverse current. This is minus VR. VR means reverse voltage. Okay, so negative axis, and this is also negative axis for particular voltage. For example, 75 degree centigrade voltage. So 25 degree centigrade voltage, let us say. So 25 degree centigrade temperature at particular temperature. So this is 25. So the reverse saturation will be here. Similarly, if you increase the temperature, so the reverse saturation current also increases. This is 75 degrees centigrade. So with this VI characteristics, we can say that the temperature affects the diode current equation, particularly reverse saturation current. So reverse saturation current increases means there is a chance of breakdown, because in reverse, diode cannot be operated in reverse bias. If you give too much reverse voltage, there is a chance of breakdown. So once breakdown takes place, your diode gets spoiled. Okay, so therefore we have to give proper temperature. Okay, so this way you can calculate the what is the temperature effect on the reverse saturation current. So in many ways you can calculate the reverse saturation current, which is given by this expression on different temperatures. So temperature increases means obviously the characteristics of semiconducting material changes, because electron hole pair generation will be increased because of the increase in the temperature. So when temperature increases, there is a chance of getting electron hole pairs. So electron hole pairs increases means what? Obviously, there is a movement of electrons. Movement of electrons. Movement of electrons indicates what? Flow of electrons. Flow of electrons means what? Current. Flow of electrons means current. But in this, because the temperature particularly affect the immobile ions. So if you see this is your PN diode, P type, N type. Okay. So immobile ions will be presented here. Okay. So when temperature increases, so we know that the potential barrier is there. Okay. So immobile ions will oppose the flow of holes from this side to this side, and this immobile ions will oppose the flow of electrons from this side to this side. So this acts like a wall, potential barrier or space charge region. Space means what? Empty. So there is no space. There is space means what? There is no charge carriers for the current conduction. So such immobile ions will be activated when the temperature increases. When the temperature increases, these immobile ions get accumulated or get energized, and they try to move from one side to another side, and that constitutes a current. So therefore, the temperature affects on reverse saturation current. So when temperature increases for a particular current, I1 is at temperature T1, I2 is temperature T2, then how to calculate with this equation. Okay. So this is the expression for diode reverse saturation current when temperature increases. Okay. And this concept is common to both silicon and germanium. Only thing is, silicon can withstand up to 175 degrees centigrade. The silicon semiconducting material can withstand up to 175 degrees centigrade, and whereas germanium can withstand up to 75 degrees centigrade. With this, hence silicon is mostly used. So it can withstand up to 175 degrees centigrade. So without breaking the reverse breakdown, and then germanium is costly and very less importance given to the germanium. Okay. So what we have seen today's session, let us see. So here in the previous session we have discussed some exercise problems on diode current equation and exercise problems on diode resistance. So what do you mean by this diode current equation? We know. So I is equal to I naught into e power v by eta vt minus 1. So for forward bias we neglect this. So simply we can write I is equal to I naught into e power v by eta vt. For simplicity we neglect this 1. And similarly diode resistance. How to calculate diode resistance? So diode resistance is in forward bias, it is eta vt by I naught into e power plus v by eta vt. And what about RR? In reverse resistance, in reverse bias direction, we have to change this polarity of the applied voltage. Eta vt by I naught into e power minus v by eta vt. This we have studied in the previous session. And then today we discussed this temperature effect on the diode. So what is the temperature effect? For every 10 degrees rise in temperature, 10 degrees rise in temperature, the reverse saturation current doubles. The reverse saturation current doubles for every 10 degrees rise in temperature, and hence I naught 2 can be calculated after increasing the temperature. I naught 1 into e 2 to the power T2 minus T1 by 100. So, and one more important point is, in order to maintain constant current, So our applied voltage must be maintained at 2.5 millivolt per degree centigrade in order to maintain constant current to the diode. So if you are not maintaining constant current, there may be a fluctuation or breakdown takes place. So therefore, in order to maintain constant current throughout the diode, so we have to maintain the applied voltage at minus 2.5 millivolt per degree centigrade. And one more important is, so this temperature, the temperature effect is another consequence of the temperature is the reverse saturation current I naught increases 7% per degree centigrade. I naught increases 7% per degree centigrade with the temperature. So this is another consequence. Okay, and all this is common for silicon and germanium. Okay, so this is the topics so far we have covered for today's session, and next topic will be capacitance of a diode. So how to calculate the capacitance we will see in the next session. Thank you.